Okay, I think I started recording. So hello, everyone, and welcome to the first of Nordic-RSE seminar series 2022 edition. So we started this seminar series last year, and this is the first talk of the new session. For those of you who are new, so what am I talking about? So this seminar series is an initiative from Nordic-RSE. And Nordic-RSE is this Nordic Association of Research Software Engineers. We were registered officially last year, so have been officially registered for 1 year and unofficially existing for a little longer. The purpose is to bring together and support research software engineers in the Nordics, and why not also outside the Nordics, for everyone who is interested. So research software engineers or people interested in such. And to support these research software engineers, we have a variety of activities. For example, this seminar series, which we started last year, the idea is to invite people who have interesting things to say and share with the research software engineers community. And basically everyone who wants to give a talk in this seminar is very welcome to do it. So if you have something that you think is interesting, it's very likely to actually be interesting. And if you want to suggest talks for this seminar series, you can either go to GitHub, to this Nordic-RSE repository, where you can suggest a talk, or alternative, you can join us in the Zulip. So we have this Zulip code refinery stream, which has a Nordic-RSE stream, and you can chat there with us and get in touch and discuss whatever you have in your mind. And we have a YouTube channel which collects all the videos of the past talks. So if you have missed some and want to see what happened before, you can check them from our YouTube channel. And we're also active on Twitter. So if you are interested in following the activities, you can follow from Nordic-RSE Twitter or from the Code Refinery stream. And if you want to join the association, you can do it by following this form. That being said, our talk today is from Brad Chamberlain from HP. He is the lead developer of the Chapel programming language, and he will talk about the Chapel and how it can help making parallel programming and working with supercomputers more productive, and I would add also more fun. So, and if you have any questions for the speaker, you are free to ask them, interrupt, and speak up, or alternative, you can write them at the bottom of HackMD. So if we click this pencil icon, we go in edit mode, and here we can ask questions. And everyone can answer. That being said, Brad, the floor is yours.
All right, great. Let me just get my screen share going here. All right. Yeah, so my name is Brad Chamberlain. I am one of the founding members of the Chapel project. It started at Cray. Cray is now HPE, and we've continued the project there. And I really liked the icebreaker question today, because it's always useful when you're talking about something that you think is productive to understand, productivity means different things to different people. And so a lot of times, whether something's productive or not depends on whether or not it helps with things that are perhaps painful or awkward or unfortunate about our current practices. And so looking at the answers that people gave, I don't know if they're visible on the video, a couple of them are definitely things that Chapel is designed to help with, reducing the amount of boilerplate required to do parallel programming, insulating programmers from rapid changes in architectures and supercomputers, going from one compute node or like a laptop up to a supercomputer really trivially. Those are places I think Chapel really excels. Hopefully you'll come away from the talk with some sense of that. A couple other things that were mentioned were debugging and profiling. I would say that Chapel's a language and a compiler, not a new tool, so it probably doesn't bring great new advances there. But I will say that because the programming model itself is simpler, I think it probably typically for most of us makes the debugging and profiling a bit simpler as well than using conventional techniques. And the last one here was changing floating point rounding modes in a thread-safe way. And whoever typed this, I'd be curious to talk to you more about that pain point, because we've recently been talking about how to best expose floating point rounding modes in the language. We don't have a lot of experience within our team with deep floating point issues like that. And we'd be very interested in feedback from users to make sure we don't do something that continues that pain and suffering. So with that, I'll begin my talk. And as Lucas said, my preference is definitely to have you ask questions as we go. I'd much rather have this be interactive and make sure people are following me than to have you feel you need to wait till the end. To that end, I'll try to remember to pause for questions as I go, but feel free to interrupt me as well if I'm forgetting to do that or am not seeing the questions and answers going on asynchronously. All right, so with that, I'm on to my second slide just to make sure that it advanced and you're seeing it before I go on.
Yes.
Great, thanks, Luca. So what is Chapel? As you may have gathered, Chapel is what we call a modern parallel programming language. By modern, think of it as sort of something that is sort of post Fortran, C, C++, the kinds of things people typically use in HPC systems, and more informed by things like Python or Java or Swift, things we might consider more modern languages. Rust may be another example. Chapel is portable and scalable. By portable, I mean it basically runs just about anywhere. And by scalable, I mean you can write a Chapel program, debug it, get it running on your laptop. You can even simulate running it on distributed memory on your laptop. And then you can recompile it and run it on a cluster or a supercomputer. Our users have found that a really effective way to develop their code and have been really impressed with how supercomputer ready they can become without ever touching a supercomputer. It's also an open source project. The development and code base is hosted at GitHub. And like any good open source project, it's collaborative. So I think Luca has actually contributed some code back to the project, if I'm remembering correctly. And we always appreciate when people in the community help us out in that way. You can think of Chapel at the highest level of having two main goals. The first one is to support general parallel programming. And when I say this, what I typically think of is if you have some parallel algorithm in mind that you've learned about or invented, and some parallel hardware that you would like to target, you'd like to run that algorithm on, you ought to be able to do that in Chapel, or we're not yet meeting this goal. And the second goal is to make parallel programming at scale, which is to say on large supercomputers, far more productive than it is today. I'll mention that even though we're very focused on supercomputers and distributed memory computing, we've also had users who have found that Chapel's become their favorite desktop language for doing just serial programming or multi-core programming. So while kind of scalable computing is a big theme for us, if you're not a scalable programmer or not a supercomputer programmer, it may still be very attractive to you on the desktop. So to talk more about what I mean by productive, this slide sort of talks about making scalable parallel computing be as easy as Python. And I don't mean to suggest that Python is a perfect language by any means, but you would probably agree with me that it is highly popular and that a lot of people find it very clear and easy to read and write. And so we'd like to create a language that is as programmable as Python, and people have that same kind of reaction to. At the same time, it's key that we retain features that people rely on in HPC, right? If something was really easy to program, but it wasn't fast, if it didn't use your supercomputer well, that's a definite loser in our field. So we want something whose scalar code is as fast as Fortran, which I think for a lot of people still is kind of, the thing to look at for kind of fast scalar code. To be as scalable as MPI, which is how most people program supercomputers today in practice. To be as ready for GPUs as Cuda or OpenMP or OpenCL or OpenACC or one of the many things that people are using to program GPUs today. To be as portable as C in the sense that you can have confidence that you can run Chapel wherever you need to. And then the last one here, I think Luca alluded to in the introduction, we really want Chapel to be as fun as your favorite programming language. And what I mean by that is I think a lot of us get into programming because we think programming is fun. But then I would say that the number of people I've met who think that HPC programming is fun is like almost none. It's thrilling, it's rewarding, it's exciting to get those large scale results. But the actual programming, I think for most people is more a means to an end than something they enjoy. So this is our motivation for Chapel. How do we sort of thread the needle here and get this nice combination of a clear language and yet one that performs and scales well and is fun? So this is the outline for my talk today. I've just given you just a little taste of what Chapel is and why. Next, I'm going to go through some characteristics of it. I'll cover some benchmarks and applications just to kind of show you that it's for real and it's developing these kinds of performance results that I've alluded to. And then I think we'll spend most of the time, if I budget things correctly, walking through some of the features in the language just so that you end up with a sense of what the language looks like, what it exposes to users. And then I've got a couple slides to wrap up. So before I dive in, let me just pause and check to see if there are any initial questions here at the outset or any technical difficulties or anything before I proceed.
No questions so far, at least in CMD. There's a comment that it is really nice that it is so portable. So for quite some time, I thought without checking that it was only running on supercomputers, only on some vendors. It is nice that I was really wrong. So I guess just a nice praise, which is nice.
Yeah. That portability is key. To be honest, even though working for Cray and HPE, we have supercomputers available to us very readily, we do the vast majority of our development of Chapel on like MacBooks and the like. So yeah, it's designed to really run anywhere. All right, so with that, let me go on and talk in a bit more detail about some Chapel characteristics. The first thing I'm going to do is just put some Chapel code in front of you, because if you're a programmer like me, I think there's nothing more frustrating than sitting through a talk and not really having any idea till the end, or maybe not even then, what the code in the language looks like. I'm not going to walk you through these programs in detail here, but by the end of the talk, I think you should have the tools necessary to understand them. This first one, and I should say this is a complete Chapel program, so you could type this into your favorite editor, save it, compile it. And this is basically just a little hello world program that's very explicit in how it creates tasks and talks about distributed memory computing. And these, whatever it is, 7, 8 lines, can basically be used to drive all of the cores on your laptop or all of the cores across your whole supercomputer. So down here at the bottom of the slide, I show how we compile it. Chapel uses a command line compiler like GCC, if you're familiar with that, or Clang. It's called CHPL, Chapel. So we just compile the program and then we can run it. And then this num locales flag here essentially says, how many compute nodes would you like to run this on? And I'm saying, let's run it on 4. And if each of those nodes had 4 cores, I'd get 16 messages out. And again, each core would effectively be printing out a message just saying hello in parallel. And you can see they're unordered because I haven't done anything to synchronize those messages at all. Okay, so that's kind of your first example. A second example that uses what we call higher level features of Chapel, although hopefully you find these pretty high level as well. This one is declaring a distributed array and then doing a parallel computation across that array, basically just initializing the elements to a simple function of their coordinates I and j. This is another complete Chapel program, so you could, again, save this in an editor, compile it, and run it. And again, it'll use all the cores across all the nodes of your system. Down here at the bottom, again, I just show a sample compile and run. Here I'm just running for a very small problem size, so it fits in my screen here. But again, running across 4 nodes, and yeah, it all, a very concise way to drive the parallelism on your system. So again, just kind of throwing some code at you to give you a flavor of the language. It's probably a lot to take in quickly. And again, I don't mean to imply it's self-explanatory at this point, but again, we'll come back to it later on in the talk and talk about some of these concepts you're seeing here in more detail. Before I get there, though, I want to start with just some characterizations of Chapel. This sort of addresses some frequently asked questions we usually get from programmers and sysadmins about it. So the first one, I'm just going to talk about some characteristics. The first characteristic is that Chapel is a compiled language. I guess we saw that on the previous slide. We do this to get the best performance possible, right? When languages are interpreted, the performance is often much lower. They can be JITted. We don't have a JIT story for Chapel yet, although we're trying to add one. So today, think of Chapel as being a compiled language, like a traditional language, like, again, Fortran, C, or C++ being good touchstones there. It's statically typed. You may have noticed in my previous code, I didn't have a lot of type declarations. We'll see that again later on. That said, the compiler is still figuring out the types of everything. So it's basically a programming convenience. But this is basically, again, to get performance and to avoid simple errors where maybe you have a typing error that only shows up after hours of running on the supercomputer. That would just waste resources and frustrate everyone. So we use static typing as a result. Again, we'll talk more about that later on. It's interoperable. So if you have existing code or libraries in C or Fortran or Python, it's possible to call between Chapel and those languages. And we do this a lot to make use of existing libraries or just to help people get started with Chapel without rewriting everything from scratch. We already talked about how it's portable, running from laptops up to supercomputers. And we already talked about how it's open source. The main goal here being to reduce any barriers people would have to adoption, and also to allow us to leverage contributions from the community. The other thing people often ask about at the outset is about Chapel releases. So if you were to download a Chapel release, what would you get in it? You'd basically get the Chapel compiler the runtime libraries, which are how we map Chapel code down to a system's capabilities, like its network, its processors, its memory. You get a number of library modules. This is kind of like the standard library providing common algorithms and data structures. I will say at the outset, our library is not nearly as huge as like a C++ or Java or Python today, but it's something we're growing, and it's definitely an area where the community has helped contribute a lot there. You get a download of the documentation, although those are also available online, and probably most people use them in the online format. And then there's also a number of sample programs, primers, and benchmarks that ship with the release. Other things people might want to know about the release is how often we release and in what formats. So we release 4 times a year, quarterly, and you can download Chapel in a number of formats. The simplest, or most complex, depending on how you want to look at it, is you can just download the source and build the source from scratch. We also support a homebrew formula and bottle for those of you who are homebrew users on Mac or Linux. We have a Docker image, and if you have access to an HPE Cray system, your sysadmin can install a Chapel module. And then the last thing I want to say, kind of at the high level characterizing Chapel perspective, is just a little bit about our team. You're hearing from me this morning, but I represent a team of about 20 people who are working on Chapel full-time every day. We've got 16 developers and a new one starting in a couple of months, a visiting scholar from NCAR who's looking at how Chapel could be applied to some climate science problems that they're wrestling with, our manager, myself, the technical lead, and then a project lead who's essentially like a technical manager. So just wanted to give credit to those people. And at the bottom of the slide here, I've got a link to more information about our team and community contributors to the project. And that wraps up my initial section on just characterizing Chapel. Again, this is a good time for me to pause for questions, just see if there are any high-level questions about Chapel or that material I just presented. And if not, the next section I'll be going on to is talking a little bit about benchmarks and applications in Chapel.
Yeah, there was a question in the chat, and HackMD, sorry. Do we need the make files or CMake or auto tools to configure build the code when there are several files?
That's a good question. So I will say that for building Chapel itself, if you were to download the open source release, today that build system uses a combination of make and CMake, although I think we're in the process of moving over to being strictly CMake. So those are required tools to build from source. If you're using one of the pre-built versions, those requirements are, let's see, are they still there? I think they might still be there. So when you compile a Chapel program, behind the scenes, we're invoking either your C compiler or LLVM, and we do some of that through make and CMake as well. So those are probably requirements for any installation. As far as if, I think the question was probably asking more from the perspective of, if I as a user have a bunch of files I'm compiling together into a program, what support is there there? So I would say in practice, probably because of the generation a lot of us are, most of us have used make files for that primarily in the past. And that's usually pretty easy to do, though there's no built-in support in make to, make doesn't know about Chapel without you telling it a bit about it. But again, that's not very difficult and something we could help people with if there were challenges. CMake is something that as we do a lot of hiring, particularly of, I would say, younger developers, we're incorporating CMake a lot more. And I believe that some of them have been using CMake to build some of their Chapel programs. So if there were questions about how to do that, we could share that information. I am not a CMake expert at all myself yet, so I'm not the best person to talk to what that looks like. Yeah, so thanks for that question. Any other questions before I go on? All right, good?
Yeah, I don't see other questions in the chat.
Okay, great. So with that, I'm going to go on to this section about Chapel benchmarks and applications. Again, the goal of this section is essentially to, I made some bold claims earlier about being compact and yet fast, and this is to basically kind of back that up. And the first slide I have here, maybe a little bit overwhelming, and I'm not going to go into it in a huge amount of detail, but this is essentially some cross-language comparison results that we gathered by going to the Computer Language Benchmarks game, which is an open site for comparing languages using a series of small but interesting benchmarks. And what we did was scrape that data and sort of characterize the entries in each language in terms of how fast they were and how small they were relative to the other implementations. Sorry, we just had a power surge here, and I'm hoping our power doesn't go out because you're going to lose me if we do. It looks like you're still there, though. So essentially, if a language is further to the left in this chart, it means its code is smaller, more compact, fewer lines of code or fewer characters. If it is faster, it is down on the graph. So things down are the faster languages. And what you can see here is the smaller languages are probably things you'd expect, scripting languages like Perl or Python or Ruby. And then the faster languages are kind of a big jumble down here at the bottom of the chart. So if I click forward, I'm going to zoom in on that bottom part of the chart. And you can see those resolve themselves, that the things that are faster more towards the bottom are things like Fortran, Rust, C, C++, C#. But you also see that the codes tend to be much larger. And in fact, a lot of the entries in these languages are reasonably heroic, which is why their fastest entries are quite a bit larger than their most compact entries, which are often much smaller. And if we think of productivity as being sort of smaller, faster codes, I think you can see that two languages, Chapel and Julia, are sort of uniquely down and to the left here on this chart. And so that is, your first indication that compared to other languages, maybe we're being successful in having codes that are both concise and yet fast. I'll say that all of these benchmarks in this comparison are just sort of simple desktop benchmarks, either serial or maybe some multi-core parallelism or vectorization. So of the languages you're seeing here, I'll kind of boldly claim that I think Chapel is the only one that was really designed for distributed HPC computing. Go was obviously designed for distributed computing, but not used as much for high performance computing. And Fortran over time has become a distributed HPC language, but wasn't designed for that as at the outset. And for most of these languages, in order to get them at all distributed, you would need to mix in something else like MPI or SHMEM, some way of communicating between the nodes. All right, so let's move though from the desktop to some HPC benchmarks. I don't know whether you all would be familiar with the benchmarks Stream Triad or Random Access or GUPS. These are basically just two very simple computational patterns in HPC. The first one basically is testing for embarrassing parallelism or pleasing parallelism, depending on whether you're an optimist or a pessimist. And it basically is just sort of stressing the memory system as much as possible across a distributed system. The second one is about randomly updating a table that's distributed. So you're kind of doing fine-grained updates to the table in parallel as fast as possible. And what we see here on the left of this slide is the reference versions of those codes as provided by the organizer of the HPC challenge, written in C and MPI. And in the first case, there's also some OpenMP shown in blue there. So this is sort of represents the conventional way you might write these benchmarks, the way the reference versions were written. And I'm not going to walk you through the code in detail, but you can see it's enough that it's very hard to read. Here in the middle of the slide, I've basically taken the Chapel equivalents of the reference codes. So anything in those reference codes on the left, I've rewritten in Chapel here in the center. And you can see it's much more concise. Even though you don't know Chapel yet, you can probably make a pretty decent guess as to what's going on in these codes. And the reason it's so much shorter is in part by virtue of being a modern language and having learned a lot from other modern languages and scripting languages and things like that. But the other part of it is that we have designed a language that has parallelism and distributed parallelism built in as concepts, and therefore there's less code, less boilerplate, going back to the warm-up question, required to drive the system. And then over here on the right side of the slide, I've got performance graphs for these two benchmarks running up to 256 nodes of a Cray XC. So this is on like 9,000 some cores. And on the Stream Triad case, we're running two Chapel versions against the reference versions. And you can see that all three lines are more or less superimposed on top of each other. That's kind of what you'd expect. Like if you're doing well with Stream, you sort of hit the memory bandwidth limit, and there's not really anywhere you can go from there. So, happily we're doing as well as the reference version, and that's what you would hope for from any new language. For GUPS, this is a case where we actually outperform the reference version on the Cray XC. The reason for this is, to a large extent, because we've expressed the algorithm at a higher level, giving the compiler the ability to map it down to the architecture in a much more efficient way than the MPI, whereas the MPI code locks in a very specific approach and technology for doing the computation that then can't take advantage of compiler optimizations or potentially novel architectural features that are only available on the XC. And so this is a case where you can see Chapel is not only much more concise than the reference version, but also dramatically outperforming it. And this is a case that I think gives a lot of the rationale for why we're designing a language. Is when you're using libraries, compilers can't do a lot to help you out, and you sort of potentially lock yourself into specific implementation approaches. Whereas when you use a language and you're expressing the semantics of your program to the compiler, it gives the compiler a lot more opportunity to help you out and optimize things for you that you may not know about or think to optimize yourself. All right, so this is benchmarks in Chapel, and benchmarks are all well and good, but if all we had were benchmarks, maybe that wouldn't be all that impressive. So happily, we've got a number of users making use of Chapel as well, and I've called out two of our flagship Chapel applications here, and I'll talk a bit about them in more detail. The first one is what you might think of as a typical HPC scientific computing application, basically a simulation of the physical world using discretization and things like that. So this is basically a 3D unstructured computational fluid dynamics framework designed specifically for doing aircraft modeling, although my understanding is it's general purpose enough it could be used for other things like COVID particle tracing and things like that. The second one is kind of a completely different and maybe sort of more modern use of HPC, which is doing more of a data science or data analytics kind of workload in Chapel. You can think of it as almost like Pandas data frames for distributed computing, if you're familiar with the data frames mode of computing. So I'm going to talk a bit more about each of these in detail, just talking a little bit about the projects and what caused them to use Chapel. And I'll start with this CHAMPS computational fluid dynamics framework. So this is currently about 85,000 lines of Chapel that was written from scratch in about 3 years. This was written by Professor Eric Laurendeau's students and postdocs at Polytechnic Montreal. I think that they would consider themselves a small university. They're probably not a name brand university like Stanford or something like that, you may think of as a big player in this space. But what they have found is that Chapel has allowed them to really accomplish a lot despite being a smaller school and a reasonably small team. I'll mention their code is not open source, but if you're interested in computational fluid dynamics, they've been very generous about sharing it with researchers who are interested in looking at it. And if you were to ask them why they chose Chapel, I would say the two main reasons are that they found that the performance and scalability were competitive with MPI and C++, which is what they would have most likely used otherwise, and that the students found it far more productive to use. With respect to that productivity, I've got some quotes here from a keynote that Eric gave at our annual workshop, I guess it was about 1.5 years ago. And I won't read you through all of this, but basically he talks about how Chapel allowed them to reduce their code by a factor of 3, to turn it from a shared memory 2D structured code to a 3D distributed memory unstructured code, but reducing the code size in doing so. The code has grown a lot since he gave this talk, so if those numbers don't seem to match my previous slide, that's why. And what they found was that it allowed their students to go from learning about computational fluid dynamics to applying it much faster than they had been able to before, where projects that had taken students 2 years previously, they could suddenly do in 3 months. And not only that, the students were very happy. They found it fun, like we were talking about earlier. So at the bottom of the slide here, I've got a link to the talk and particularly to this quote here. But if you're interested in hearing from Eric himself or hearing more about their project, this was a great talk, and I would encourage you to take a look at it. I'm not going to go through this slide in detail, but just kind of to point out for those who might be familiar with computational fluid dynamics, I think this team is going around and participating in a lot of the key workshops and conferences in their space, competing in a lot of sort of community grand challenge style problems, and turning up results that are turning to be very competitive with sort of high profile, longer lived codes, the NASAs and JAXAs and academic institutions of the world. And so I think it's really notable how much they've been able to do in a short period of time. And I'd like to think that in addition to their skills, Chapel had some role in that. With that, I'm going to go to the second example here, Cuda, and I'll pause for questions again after this Cuda run through. I apologize, I haven't done it before now. So the idea behind Cuda is some users wanted to do data science in Python on large-scale supercomputers. Now, if you're familiar with Python, Python is not really well suited for, well, arguably for performance programming at all, but particularly for kind of large-scale parallelism. So kind of their motivation here was, you've got some data science problems that require HPC scales to solve in a reasonable amount of time. and you've got a bunch of Python programmers, and you've got access to HPC systems. So how will you leverage your Python programmers to get this work done? Again, given that Python doesn't really scale and that these programmers may not have the skills to program an HPC system in, C++ and MPI or something like that. And so what they ended up doing was writing an Cuda client that was written in Python, and a user basically will interact with this client like any other Python library. In fact, the client basically exposes a subset of the NumPy and Pandas interfaces. So if you were like a NumPy or Pandas user, you might be sitting in your Jupyter notebook, making calls that you thought were sort of normal NumPy or Pandas routines. And what's happening is where NumPy and other Python libraries are often implemented in C or C++ under the covers, what they did was implement the implementation in Chapel. And so there's this client server model where when you say something like add my 2 arrays, that command is shipped off to the server where those arrays are stored, potentially in distributed memory. The arrays are added, a result is returned back saying where the result lives, and sort of the Python programmer, again, is interacting with Python, potentially unaware that they're sort of driving a supercomputer, except for the fact that they're running such large problems at such speeds that, it's pretty evident it's not just running on their laptop. So that's the model behind Cuda. Again, leveraging a very common model for Python of implementing fast code in other languages, but here using Chapel rather than C or C++ in order to get the advantage of scalable computing. So let's see, I've talked about a lot of this. I guess I'll just say on this third bullet here that what they found and their goal here was to compute massive scale results, think like dozens of terabytes of array data, sort of fast enough that you as a human are sort of interacting with it and don't lose your thought process. Like you don't find yourself constantly going to get coffee because it takes 5 minutes or half an hour to get things done. And so for most of their key operations, they find that things finish in seconds, or at worst, a small number of minutes, maybe 1 or 2. Cuda is currently about 25,000 lines of Chapel. There's also a lot of Python code, which I don't have the counts for offhand. Again, written more or less in the last 3 years. This was written by Mike Merrill and Bill Roos at the Department of Defense in the US. And happily, it is open source code. So if this model of having Python-based programming, supporting NumPy or Pandas, and running it on a supercomputer is appealing to you, you can download Cuda and either use it yourself with the features it provides, or there's also the capability to add in new features yourself. So if, for example, NumPy and Pandas weren't interesting to you, but doing FFTs was, you could sort of add a new FFT module and do interactive FFTs with it. So it's designed to be extensible in that way. If you were to ask Mike or Bill why they use Chapel, the first thing was they had to get this done quickly. So they wanted a productive language, and Chapel was, again, high level, but gave them the performance and scalability they needed at the end of the day. They really liked that it was close to Pythonic, both because it let them write Cuda very rapidly, but also because since they're appealing to Python users, if that user needs to get under the hood and make changes themselves, they're not appalled by what they see. Even though Python is not the same as Chapel, Chapel is, clean enough or familiar enough with its concepts that they found that Python programmers can go and kind of add new capabilities and program the supercomputer directly if they need to. And then again, this capability to develop on the laptop and then apply it on the supercomputer was key for them because they don't always have access to their supercomputers, at every moment of the development cycle. I've got just a couple performance results from Cuda. This first one, again, is a little bit overwhelming, but let me just say that the columns here, the first one is basically, vanilla NumPy. The second one is Cuda running just on a single core, so kind of the closest equivalent to NumPy. The next one is Cuda on a multi-core, so a single node 36-core run. And the last one is kind of a massive scale 36-core on 512 nodes run. The problem size, I should say, takes a jump between the shared memory and the distributed memory cases. And basically, the rows here are the key operations in Cuda, the place where most of the time tends to be spent or most operations are based. And you can see sort of the factors improvement here, where even with a single core, we sometimes get factors up to 2 over vanilla NumPy. But as soon as we use multiple cores, we've got sort of 3 to 16 times better performance. And when we go to distributed memory, we have hundreds and thousands times better performance. So again, much more scalable than traditional NumPy. And even maybe a benefit on the desktop if you're just a NumPy user. And then one of the things, so I guess I kind of said, these are sort of the key operations. The sort is kind of probably the most important operation for the Cuda users today. So one of the things we've been working on is making the sort as fast as possible, scaling it as best possible. And this is a result we ran last summer on a large HPE Apollo system that we had access to that had 73,000 cores of AMD Rome. And we basically sorted 72 terabytes of values in 2.5 minutes, achieving 480 gigabytes per second. And I think my favorite part about this is this was done in about 100 lines of Chapel code that were essentially transliterated from kind of a high-level pseudocode sort implementation of radix sort. So I'm not a sort expert, but I'm told that this is close to world record sort performance. And I think if we took it as performance per line per code, it would almost certainly be a world record, although nobody really seems to measure that. I'll also mention anecdotally that in the past couple of weeks, we've gotten access to an even larger system. I think it has 100 and some thousand cores, or at least that's how many we ran on. And we got up to 1,200 gigabytes per second. So we've both improved the performance since this experiment last summer and scaled out to even larger scales now. Again, because this is sort of the workhorse for a lot of our Cuda operations, having this be super fast allows a lot of other more interesting operations like group by to also be super fast. All right, so that's my review of Chapel benchmarks and applications. And again, sorry, I've gone a little bit long without pausing for questions. Let me stop here and see if any questions have come in since my last break.
I don't see any new questions in the HackMD nor in the chat. I don't know if there are questions from the audience at this stage.
Okay, great. So not hearing any. Again, feel free to ask questions as we go. The next thing we will be doing is talking a bit about the Chapel features themselves. So taking you beyond kind of the glossy high-level material I've been showing you and showing you a bit more about the code itself. When I teach Chapel concepts, I tend to think of the language as sort of sorting into these 5 categories of concepts, from higher level things like data parallelism down to lower level things like control over locality on your system. So I'm going to use this kind of as a roadmap during this part of the talk. And I start with what we call lower level Chapel. We saw an example of this earlier on. And in particular, I'll start with the base language. And what you can think of the base language as being is if you were to take Chapel and remove all of the features related to parallelism and all of the features related to locality or scalable computing, what you'd be left with. So kind of like the serial language part of Chapel, if you will. And this is mostly to make sure you understand the rest of the code examples going forward. I'm going to do this in the context of computing a Fibonacci sequence. The Fibonacci sequence is admittedly a completely, well, in my experience at least, a completely artificial example. Not very motivational for real-world computing, but it has the benefit of being short and illustrative of some Chapel concepts. It's also quite simple. If you happen not to be familiar with the Fibonacci sequence, basically it starts with the numbers 0 and 1, and then you add consecutive pairs of terms to get the next term. So 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, and so on and so forth. All right, so let's look at this code in Chapel. So here on the left, I've got the Fibonacci computation written in Chapel, one way of writing it at least. And again, I'm going to use this just to introduce some concepts in the language as we go. Over here on the right, I show, again, if how you would compile this program if you have it saved. Again, this is a complete program, so you could compile it like this and then run it. And if you ran it, here's what would happen. The first executable code we hit is this for loop. The for loop is quite a bit like for loops in other languages, except rather than taking low and high bound necessarily, as in C, we basically take something we want to iterate over. In this case, we're going to iterate over this iterator called fib. An iterator in Chapel is basically like a procedure or a function, but rather than just returning a single time, it yields values back. And so each time it yields a value, the loop will be executed for that value and then continue. And I think I actually illustrate this a little bit here. So we would start running this fib iterator. When we hit this yield statement, we would yield that value back. It would be bound to F. We'd run the loop body printing out F, and then we would continue from where that yield left off until we hit the next yield, and so on and so forth. Eventually, we'd drop out of this. That would terminate the iterator and exit us from this loop and go on to the next statement. You also see a for loop down here within the iterator. This shows maybe a more conventional for loop where I'm just iterating over what we call a range in Chapel, the numbers 1 through X. Sorry, I forget I have callouts for all this. So yeah, so we yield a value, then we execute the loop body for that value. We're printing out 0, for example, the initial value. Then we continue with the iterator from where it left off, and we repeat until we fall out. So we just keep generating the first n Fibonacci numbers. All right. So the other thing I skipped past here at the top is we have these configs built into the language. These are basically declarations that support command line overrides. So here we're saying, give me a constant named n, initialize it to 10, but then this config essentially gives us built-in support for overriding that default value. So for example, if I rerun my program saying, Windows in the way, --n equals 1,000, basically it would run that program for the value of n equals 1,000, and I'd get the first 1,000 Fibonacci numbers. So these configs are essentially a way to avoid doing manual command line parsing, although you're able to do that as well if you prefer. Another thing you might notice in this code, I mentioned it earlier, is that there aren't many types declared here. Like I've declared n, but I haven't said it's an integer, or haven't declared the type of f or I, the loop index variables, or the argument type or return type for my iterator, or the types of my local variables, current and next. So again, even though I haven't specified the types, each of these symbols has a very well-defined type, and the Chapel compiler will essentially infer these. So for example, when it runs, it says, well, I know that 10 is an integer, so n must be an integer as well. And then it says, well, if fib is being called with an integer, then this argument x must be able to be an integer as well. So I'll make x an integer, current next are inferred to be integers, I is inferred to be an integer, we yield integers, so f is inferred to be an integer. Basically, the type information just flows through the program during compilation. If you prefer, there are a lot of cases where actually describing types of things can be good documentation or make your library interface more stable. So there is the ability in Chapel to specify types as well. And so this is a version of the code where I've gone in and specified a bunch of types. And as an integer, fib takes an integer and yields integers, and so on and so forth. But usually in my slides, I use the type inferred code just because it's a little bit shorter, a little bit less cluttered, and usually sufficiently clear. We also have zippered iterations. So in this first version I've shown you, I'm just iterating over a single thing. But if I change the code, I can put this zip in here, which allows me to iterate over multiple things simultaneously. So in addition to my fib iterator, I've mixed in an iteration over another range from 0 to n-1. And this allows me just to make my output a little bit more descriptive. Fib number I is f. And so if we were to rerun the code with that, you'd see, slightly more descriptive output. And so this ability to zipper multiple things together and iterate over them simultaneously is really important. And we support that both for serial loops like this one, and then parallel loops, which we'll see in a little bit. I already mentioned in passing these ranges. These are essentially just a way in the language to represent a regular sequence of integers. These are used a lot, both for driving for loops like we're seeing here, but also for things like defining multidimensional rectangular arrays and slicing and dicing them.
So there's a question.
That's my fib example. Yeah, sorry, go ahead.
Yes, sir. Yeah, there's a question in the chat. Does restricting types affect efficiency or binary size, or is it, or is this to help humans and catch errors?
I would say it's both. Definitely probably the primary concept is the performance aspect. So when you're in a dynamically typed language, usually that carries a performance hit with it. And again, performance is what we're all about at HPE and Cray. So that's probably our first motivator. But the second one is an element of safety. If you did something here like, I don't have an example off the top of my head, but did something that sort of made the types incompatible, did something illegal, like tried to add an integer in a string or something like that, the compiler would warn you about that and you'd get an error. Whereas if that were a dynamic issue, again, you might run for hours on the supercomputer and only then hit the error. And that could be a waste of resources and very frustrating. So I would say it's a combination of both, although again, performance was probably our primary motivator in supporting the type inference. Any other questions here while I'm paused?
So I don't know if that's what, I mean, the way I understood at least the question was more like if annotating types instead of letting the compile infer themselves affects performance or binary size. I don't know if it was the original question, but then that's at least the question that arose now for me.
Yeah, that's a great question. So right, the difference between the version of my code where I specified all the types and the ones where they were inferred will end up being the same. So there is no performance or correctness difference between those two. Essentially, as long as the program compiles, it will be type safe. And any annotation of types you do would be primarily either for yourself as a programmer to kind of reassure yourself, like, well, I think I've written fib to take an int and yield an int, but let me just assert that that's the case. Or potentially as documentation to other users. Like if fib were meant to be part of a library, probably that library would be more effective if it sort of expressed what the constraints of fib were. In this case, actually, yeah, fib would actually need to take an int because we're looping over that range. So yeah, so being able to say like x must be an integral value might be valuable constraint for a user of that. But yeah, no performance or correctness changes between the typed and untyped versions of the code. Thanks for clarifying the question for me. That's an even better question.
Out of curiosity, do you need the type annotation, for example, for recursive functions? Like in some languages, type inference is more difficult for recursive functions. So
yeah, that is a good question. Recursive functions are an area where sometimes we need type annotations today. I think in particular, if your recursive function is returning an array, I'm pretty sure that's a case where we require an explicit type today. I think if it's a simpler return type, like just an integer, and if the control flow of the recursive function itself is pretty clear, I think we can infer those cases still. I'd have to check that. But yeah, admittedly, recursion is a little bit trickier. And there are cases where we can't always infer that today. Any other questions here before we go on?
Seems clear to go.
Okay, great. So again, this is just my very simple example to give you some of the base language features. I will say the base language itself is kind of massive. If you think about, we're trying to be as productive and competitive as a Java or C++ or Python or whatever. You know, all these languages have a lot of features, and Chapel has a bunch of those features as well. So we could spend probably a whole day talking about the base language and not talking about anything that makes Chapel unique. This is just my slide that calls out other things you might be interested in. It has error handling. You can do compile time metaprogramming. It supports object-oriented programming in a couple different flavors. It has generic programming. You can do overloads, a bunch of nice argument passing modes, organize your code into modules. Basically, again, all the features you'd kind of want from a modern productive language. You know, hopefully we've got them in Chapel. There's a list of a bunch of them here. But again, we're not going to spend a lot of time on those because those aren't really what make the languages unique. So instead, what I'm going to do is go on to some of the features that are more unique in Chapel, talking about how we do task parallelism and distributed memory programming. Also mentioned, I see that I'm getting close to the top of the hour. If you need to drop, totally understandable. We're recording this so you can catch up later. I'll probably go just a little bit over the top of the hour, and then I'm happy to hang around if there are additional questions. But I want to at least get through these features that make Chapel a bit more unique before stopping. And we are pretty close to the end of the talk here. So before I get into task parallelism and locality, these lower level features, I'm going to define something I mentioned very briefly earlier on, which is this notion of the locale in the language. Think of a locale as basically a chunk of the target architecture that can run tasks and store variables. So basically something that has memory and processors. And on a typical HPC system, it would be reasonable to think of a locale as being like a compute node. So if I was running on 100 locales, maybe I'm running on 100 compute nodes in my cluster or supercomputer. We saw earlier when you run a Chapel program, you can specify the number of locales on the command line. So here I'm saying run on 4 nodes. If I said num locales equals 100, I would run on 100 nodes. And that's how you sort of request the system resources and get the program started on those resources. And then within the program source code itself, you have access to this built-in array called locales. And this represents the compute nodes in which you're running on. So again, if I were running on 4 locales, my program would be populated with this array of 4 locale values. And that gives me an ability to talk about the nodes on which I'm running, query them, find out things about them, like how much memory do they have or how many processors do they have, and specify where I want my code to run. So we'll see that be used in my next example. The one other thing I'll call out here is when you run a Chapel program, it starts running as a single task on Locale Zero. And then from there, additional parallelism is added to the program through language concepts like we'll see. But we start out running on Locale Zero whenever, your main, if you will run on Locale Zero when you run a Chapel program. So this is what I'm going to do is build back up to that parallel hello world we saw before by introducing these concepts to you. The first thing I want to point out is this built-in identifier here. This is kind of a built-in variable that refers to the locale in which you're currently running. So at the beginning of your program, you're running on Locale Zero. Here would refer to Locale Zero. And what we see is that you can make queries from here, like this first query, max task par, basically says, how many tasks can I run in parallel on this locale? And you can think of that as giving you like the number of cores or number of threads that are available on that node to run tasks. So if I run a 16-core processor, this would return 16, and I'd store that in my numTasks variable. The other thing I'm doing in my loop here is querying here.name. That's essentially like, what's the name of this locale? You can think of it as being like the host name in Unix terms, but basically just a unique identifier describing that locale or that compute node. So the key to this program is this co-for-all loop. This is like the for loop we saw before, but it is parallel. So think of the co-for-all as saying it's a parallel loop, and the co is maybe meaning it's a concurrent loop. And what the semantics of this loop are is that every iteration will be executed by a distinct task. So again, if I were running on a 16-core node, numtasks would be 16. My loop is counting from 1 to 16 here, but the co-for-all is going to say each one of those 16 iterations should be executed by a distinct task. So when I compile and run this, if I were just on a 4-core system, I would query that there were 4 cores, I'd create 4 tasks, and each one would print out this little hello world message. Because I haven't done anything to coordinate between those tasks, they're going to run in an arbitrary order, and so the output's going to come in a mixed up way, or in, I should say in an unordered way. But happily, these prints will be atomic with respect to each other. So you'll never see like one task print hell and then the next one start printing, right? Each one will be distinct, but potentially in any order. Now, what I've shown you so far is only a shared memory program. I mentioned that we start running in Locale Zero, and nothing I've done here has said to use any of the other locales. By default, a co-for-all is only going to use the resources that the thing that's being iterated over are mapped to, and ranges are always local in Chapel. So I'm basically running using multiple cores, but if I were running on 100 nodes, I'm never using any of the other nodes. But with a simple change to the program, I can change it into a distributed memory version. This is what we saw earlier in the talk. The first thing I do here is refer to that locales array we talked about earlier. So again, if I'm running on 4 nodes, I'd have an array with 4 elements, and this outer loop will take 4 iterations, 1 for each node. So I use a co-for-all to create a task per node, essentially. And then I use this on clause, which is a way of taking a task and logically moving it somewhere else. And so here I'm saying each task should run on its respective locale. And if you're familiar with SPMD or single program multiple data programming in HPC, like MPI, where you run main and run a bunch of copies of main, at this point, we've essentially done that same thing. We've kind of run a copy of the body of this loop for each of our compute nodes by creating a task per compute node and saying to run on that compute node. At that point, each task on the compute node is going to run the shared memory code that we started out with, query how many cores are on that compute node, start up the inner co-for-all, it creates a bunch of tasks for those cores, and basically drive all of the cores on its node. Because we're doing this across all nodes, again, we're driving all cores across all the nodes that we've accessed in running our program. So if I change my execution line here to say num locales equals 4, and again, if I'm on a 4-core node, then I'd have 16 messages come out, and you can see that they are now differentiated by the different locale names in the right-hand side. Again, because there's no synchronization between these tasks, they'll come out in an arbitrary order. But if we needed those to be synchronized, there are ways in which you can synchronize through variables in order to make sure that things are coordinated between your tasks as needed. All right, so that's kind of your very quick introduction to, again, the low-level features in Chapel for creating tasks and for saying where on a distributed system those tasks should run. Let me pause here and see if there are any questions about these features or this example before I go on.
I don't see any questions or typing in HackMD at the moment.
Okay, great. I'll say, actually, before I go on, these low-level, like when we talked about the base language, I talked about how there were a bunch of features I didn't have time to show you. In the task parallel world, there are only a few other things that you haven't seen. There are a couple of other ways to create tasks. There are these special variables I mentioned that allow you to synchronize between tasks. We call them atomic or sync variables. And that is about it. So you sort of know a good fraction of what you need to sort of create parallel tasks across a distributed system in Chapel today. But what we'll do next is go up to the higher level features in Chapel and show how it can be made even simpler for operations that can be described as things like do a bunch of operations across an array or across a distributed index set or things like that. And again, this is what we consider higher level Chapel. So what I'm going to do here is essentially declare a distributed array and then fill it up with semi-arbitrary values that are just a function of its row and column coordinates. The second line, but the first one I'm going to talk about here is this line that declares this constant d using these curly brackets. This declares a domain, which is like a first-class concept of an index set in the language. So you can think of it as like almost like an array, but rather than having data associated with each index, it's really just the indices themselves. So you can think of it as like the size and shape of an array, or even the size and shape of an iteration space, if you like. And we'll see how that's used in a moment. The first thing is that we use these domains or index sets to declare arrays. So here, for example, I'm saying, give me an array A whose indices are defined by D, so a 2D n by n array. And the element type of this array is real. So at each of those indices, allocate a floating point, a real floating point value. And so now what I've got is this n squared array with data associated with each index, like you're used to in other languages. The other thing we're going to do is use the domain to drive a loop. So here we have a third form of loop, the for all loop. It's another parallel loop. Unlike the co-for all, though, it's not going to create a task for every iteration. If I had this problem size of 1,000, I'd have 1,000,000 iterations. Each iteration is only doing a little tiny computation. So creating 1,000,000 tasks would be overkill. I'd basically spend all my time creating and destroying tasks rather than getting computation done. So what the for all loop does is it says, use an appropriate number of tasks for this thing I'm iterating over. In this case, D. And so in practice, what D is going to do is say, well, how many cores am I running on? Let me just distribute the iteration space across those cores, and I'll sort of create a number of tasks equal to the number of cores and have each one do a subset of the problem. Okay, so this is sort of the second use of domains. We use them to drive these parallel loops like this. So here's the short example of compiling and running it I showed before. Again, running it for just a very small problem size, so it fits on the screen here. But if I were to run this on my 4-core laptop, for example, these 25 elements would be divided up across those cores such that each core did just a subset of those array assignments, and then we would all print out the array at the end. Now, like the previous example I showed you, this is a shared memory program so far. Again, I start running on Locale Zero, and nothing I've done here, there are no on clauses, so I haven't explicitly said to run anywhere else. And because of the way I've declared this domain and array, nothing about the domain and array themselves are distributed. So again, if I were running on 1,000 nodes, I would never be using any of them other than the initial node with the code as it is. But as with the previous example, and here's my picture of that. If I were running on multiple locales, D would be allocated in Locale Zero, A would be allocated in Locale Zero, and all the other locales would just not really have anything to do. But as with my previous example, with just a few small changes here, I can essentially turn this from a shared memory program into a distributed memory program. And so essentially what I've done is add 2 new expressions here. The first one uses the cyclic disk module, which is one of a number of standard distributions that we support in the library. And then the second is to apply to my domain this recipe to say to map it down to the locales using a cyclic distribution and start by giving index 1, 1 to Locale 0. So these domains basically say, domain maps like cyclic say, how should the domain's indices be implemented? And how should the array's elements be stored? And how should a parallel loop be executed across these in terms of all the target locales? So let me show that with an illustration. If I were to run this program on just a single locale using the num locales 1, the cyclic distribution basically is completely degenerate. Locale 0 is going to own all of the elements, and so it'll own all of the data and all of the iterations of the loop. And because this computation I've written is independent of the number of locales, it's just a function of I and j. If I add more locales here, basically I change the implementation of the program, but the output of the program is identical. So you can see I still have that same matrix being printed out. But when I run on 4 locales here, what happens is that cyclic distribution cyclically distributes the indices of D, and the array elements of A, and also the iterations of my loop here, such that now each locale owns a chunk of the array and a chunk of the iterations. So my for all with these two little changes has basically turned from a shared memory multi-core for all into a distributed memory, use all the cores of all those nodes version of for all. Now, if I were to rewrite the loop body here to make it sensitive to where I was running, so I've changed it from a simple computation of I and j to one that also takes the locale's ID into account. Here, the results are obviously going to depend on which locale is owning the iteration. So again, if I'm just running on one locale, the locale ID there would be 0. If I add 1 to it and divide by 10, that gives this 0.1 in each of my places, which says the initial locale ran all of those. But if I run on 4 locales here, each locale is going to plug in its own ID for that here.id field. And so you see that the results start changing to show that locale 2 did some of these and locale 3 did some of these and so on and so forth. So that just kind of shows that sometimes for all loops, if they're just kind of pure math, are independent of the number of locales you're running on, or you can make them sensitive to the number of locales you're running on it if you desire that. And that is my quick introduction to data parallelism in Chapel. This is another area where there are a lot of other things you can do. There are reduction operators, different array operators you can use. So sort of it's a very rich array language, but hopefully I've given you a flavor of some of the basic concepts here. And let me pause one more time here for questions before I wrap up.
Yeah, so there are a few questions at the moment. Okay. So are domains a unique feature of Chapel, or is there equivalent in other languages? And this also has the comment, I like how they guide me towards not going out of bounds, like appreciation of domains.
Yeah. So I would say domains are reasonably unique to Chapel. Definitely, we've taken the domain concept much further than previous languages have. The concept for domains came out of a language that the team I worked with in graduate school, so we worked on a language called ZPL, and it had a concept called a region that was a lot like the Chapel domains, but not nearly as powerful and rich. So that was kind of the basis for our domains in Chapel, but it also pointed out to us a lot of the limitations of our original ideas that we were able to improve upon when we came to Chapel. And I think those improvements have made it much better by leaps and bounds. Going back even further, the high-performance Fortran language that was developed in the 1990s had a concept, I think they called them templates, that were somewhat similar to domains and regions, but they were not nearly as first class. But that would be another kind of historical antecedent for it. I think that this concept has become, you see it show up a little bit from time to time in maybe not languages, but sometimes I think libraries have now had a similar kind of concept of a distributed index set object. But I'm having trouble coming up with a great example off the top of my head. I guess back to my original statement, I think that domains are much more kind of robust and first class in Chapel than any other programming technologies I'm familiar with.
Yeah, thank you. So next question is, what's the logic how indices are distributed over locales?
Yeah, so basically that's what this dmapped clause is. So dmapped you can think of as being short for domain mapped. Again, the domain is the index set here. The question is, how do we map those down to the locales? And this cyclic is sort of one of several different recipes that you can use to do that mapping. The library has some others, like you can block the nodes, block the indices between the locales. There's a block cyclic distribution, but it's admittedly not very good yet. We also have the ability to have sparse arrays and to distribute sparse arrays. So essentially, this dmapped clause says, how should I map the indices to the locales? Where in this case, we're saying we'll do it in the cyclic round robin fashion. And then it also says things like, how should the array elements be laid out in memory? And when we have a parallel loop like this for all loop, how should those iterations be implemented? Should they be local? Should they be distributed? Use multiple cores, use a single core? So essentially, think of this domain map cyclic or other expressions you could put here as being a recipe for how to implement an array in Chapel, or in this case, specifically a distributed array in Chapel. Those domain maps are themselves actually written in Chapel. So if you had some new distribution in mind, our community uses recursive bisection a lot, and I see that Chapel library doesn't have a recursive bisection distribution. You could actually write Chapel code that would implement a distributed array using recursive bisection and plug that in here without any changes to the compiler or the language. Now that's a very advanced and not very well documented feature of the language, but the point is that the implementation of arrays is not built into the language itself. Like the compiler doesn't really have any special knowledge about cyclic or block distributions, but there's something that are kind of part of our library and an extensible part of the language. That in itself is a pretty interesting and complicated topic that we could easily spend a whole hour on, but hopefully that gives you a flavor of the flexibility that's available here and maybe a little bit more about how cyclic specifically works. But if there are any follow-up questions there, I'd be happy to take those as well.
Yeah, interesting. I can go through the previous question, then we can see if there are follow-up questions. So there was tier one. Does Chapel have built-in feature support for GPU programming?
Yeah, that's a good question. If anybody wants to stick around, I have some backup slides that talk about GPUs. I will say that over the long term, we have not traditionally had support for GPUs, and the support we have today is still in a prototype fashion. But we do have some support for GPUs, and it uses a lot of the same concepts you've seen so far. So for example, there's an ability to say like on my node's GPU or on the third GPU on my node or things like that, using the same on clause we saw before. You can essentially target a chunk of computation to a GPU or a set of GPUs. And then within that code, if you use the same kind of for all loops or a for each loop, which is another loop form we haven't seen today, those parallel loops will essentially be executed in parallel using the GPU's lanes and things like that. So again, I want to put in the caveat that this is very new support. So we've got people using it a little bit, but it's not difficult to run into cases that either don't work in the sense that they don't actually execute on the GPU, even though you wanted them to, or sometimes it even just breaks the compiler. We're working fast to make that better and better as fast as we can. But if you'd like to try it out, we're definitely in a position today where there's enough there to be interesting. And we're very interested in feedback from users who are interested in using Chapel on GPUs to see what's working or what's not working for you and where we could improve things to make it better for you in the short term. Again, I do have some slides that illustrate a little bit of what I've talked about. We'll finish the Q&A first, and then if anybody is interested, I'm happy to go through those slides and just give you a little bit more of a visual to the answer I just gave.
Yeah, okay. So I can write in HackMD a small poll if like people have time to stick around, and like if they want to could you stick for GPU slides? So people now can vote on HackMD if they can stick around, then we can see how many people can.
Great. And any other questions in the queue at this point?
Not at the moment. Not that I can. Yeah, maybe you can wrap up the slides and then we can go.
Yeah, so let me wrap up. I've just got 2 slides here. First one is just a summary of what I've been telling you about today. I'm asserting that I think Chapel is unique among programming languages. I think the fact that it has built-in features that are designed for scalable parallel computing make it much more HPC ready than any other programming language, other than perhaps Fortran. It supports clean and concise code relative to conventional approaches. Hopefully you've seen that a little bit in the examples I've shown today. And it ports and scales from laptops to supercomputers, as we saw in some of these simple examples like this stream triad on the right here. As I've told you a little bit about, Chapel is being used for productive parallel computing in production applications today. Users are reaping its benefits in terms of both the productivity and the performance at large scales in large applications, and in things as diverse as kind of traditional physical simulations like the computational fluid dynamics code we saw, to things that are more data science-y, like the Cuda, NumPy, Pandas interfaces that we saw. And lastly, if you or any of your users are interested in taking Chapel for a spin, let us know. We're definitely happy to work closely with users and user groups to help ease the learning curve, get you started. Oftentimes we've found that if a user comes in with something they want to express and we come in with the Chapel knowledge and we do some pair programming, we can get them up and running in a short amount of time and sort of get them started without them having to learn everything by themselves. So that's something we're happy to do if that would be of use to any of you, or again, your users. And then the last thing I've got here is basically just a slide with resources. The first one is our webpage, and all of these other resources are available from there. We've got social media accounts if you use any of those and want to follow us, including a YouTube channel where you can watch other Chapel talks, including some by our users. We've got a bunch of different ways in which we interact with the community. We interact with Luca in some of these forums, so he's familiar with these. And I should mention, today we're going to be starting a blog, which I don't have on here yet because it isn't live yet. And we're going to be doing Advent of Code for the next few weeks, if you're familiar with that. as a way of teaching people about Chapel programming, and that'll be done through the blog. So I can send a link for Luca to share later on there, although it should be easy to find as soon as it goes live. It'll be on the sidebar here. And that's my talk. Sorry to go a little bit over. I'm glad for those of you who stuck around. And again, I'm happy to stick around if people have other questions they didn't get answered, or if they would like to see a bit more about the GPU. But again, if you have to drop or have already dropped, no problem at all. And again, I'm sorry to go a little bit over.
Yeah, thank you. Let's give a virtual round of applause. Zoom changed the interface. I cannot find the clap emoji anymore, but I can clap physically also.
Thank you very much. Yeah.
So yeah, actually about advent of code, I can chime in quickly. Also at Nordic-RSE, we are very enthusiastic. Last year we had like weekly meetups for chatting about different like challenges. So definitely, I think people from here will enjoy following also that. And also,
we just learned about advent of code last year, and I think it's an amazing website and program. And so yeah, we're excited to be able to blog about it this year, and also a little intimidated. I think it's going to be a lot of work. Doing the solutions themselves is kind of a modest amount of work, at least for the first few days, but like writing about them is going to take some time. But hopefully in doing so, we'll be able to teach people a bit about the language using examples. And if you're following along yourself, the examples will be familiar to you. So that'll be great.
Yeah, and maybe I can quickly also advertise that from Nordic-RSE side, we will probably also have this year, like kind of weekly informal meetups for advent of code. So
great.
Yeah, then there are a couple of very nice questions actually here. So, and by the way, also it seems most people will be able to join, stick around for a little more for the GPU part.
Okay.
But so there are very nice. So the first question is, what do you know about the language design development that you wish you knew when you started with Chapel 15 years ago? Or 15 question marks, 15 or whatever years ago.
Yeah. What do I wish I had known then? Well, that's an interesting question. There's definitely a ton of stuff I've learned along the way. Fortunately, we have been able to address, like I think we made a lot of mistakes in the initial design, or just had a lot of oversights, things we were naive about, features we were missing. And fortunately, we've been able to address the vast majority of those as the program's gone along. So, the things I'm most regrettable that I didn't know at the outset of the project, or that we didn't know as a team, happily are not things that keep me up at night because we've already addressed them. Trying to think about whether there are things in language today I regret. Well, there's some naming things I regret, things I had hoped to rename that we've never succeeded in renaming, but those aren't really deep lessons learned or anything like that. I guess maybe the main thing that comes to mind as a regret is, I mentioned the GPU support, and it's only been relatively recently, like I would say the last year or 18 months, that we've really started to support GPUs. And GPUs, of course, have been around and used in these high-end HPC systems for years now. So I feel like we were late to the GPU game. And in part, that was because it wasn't a priority for our users. And in part, it was because we were intimidated by how hard we were afraid it was going to be. It's turned out to be easier than we thought, which is not to say it's trivial, but in large part due to the great amount of investment in the community in the LLVM compiler. We were also late coming to the LLVM compiler framework. When we started out, LLVM existed, but it wasn't nearly the major technology it is today. And so that's something I guess it would have been nice if we had invested more in LLVM from the start. That said, by not doing that, it allowed LLVM to mature a lot without us having to mature along with it and go through its growing pains. So we probably benefited there as well. Those are kind of the answers that come to mind for me. I'm sure in a half hour I'll think of something. I'm like, oh yeah, here's something major I learned I wish I had known. But again, I think the main thing is, while we made a lot of mistakes in the initial design, we've been able to fix those as we go. And that might be a good time for me to mention very briefly, something we're working on, and something you might hear about if you come to our annual workshop, CHU, is we're working on this release that we call Chapel 2.0. And the idea behind Chapel 2.0 is that to date, our users have been very patient with us when we have made mistakes in language and gone in and fixed them. And of course, when we fix our mistakes, we're often breaking their code because we're changing the way things work. And this Chapel 2.0 release is designed to be a release in which we commit to, for the core features, like a lot of things you heard about today, like we will not break these things or change these things going forward. We'll reserve the right to change other things in language or things that are outside of the scope of 2.0. but that'll mark sort of a point at which if you or your users had any concerns about, well, if this language is changing rapidly, I don't want to have to keep updating my code. That will stop that, and that's coming up very shortly, like within the next year, we hope.
Cool, great. I really love the next question. Chapel is known for its welcoming community. What was or is the most effective trick, approach, tip when building the Chapel community?
So thanks for that characterization. We definitely try to work hard to make the community as welcoming as possible. I would say probably the most important thing about that from my perspective, or maybe it's two things. I think the first one is responsiveness. I remember when I took an operating systems course, the professor asked us whether latency or bandwidth was more important. And I sort of guessed bandwidth, but his answer was latency, because nothing's more frustrating than like doing something and then having to wait a long time for the response to come back. And I think that applies in user interactions as well. And it's difficult and time consuming, because of course you can't control when user questions will come up. But I think we definitely try to prioritize at least responding to users quickly, if not fixing their issue quickly. You know, sometimes we can, sometimes we can't. But that's sort of like responsiveness and showing that we're here, we're paying attention, has been, I think, key for us in terms of building up the community and building up a good rapport within the community, or a good reputation is what I mean to say. And then the second thing is kind of just the common senseness of, you know, trying to be polite, trying to be patient, trying to be kind, trying to not be a jerk, which, you know, we should all do all the time in our lives, but of course in online settings and when you're stressed out about your job or whatever, can sometimes be hard to do. So I think trying to maintain that, you know, that friendliness that I think we enjoy in person, but often sort of falls away in virtual interactions. You know, that's something I think our team really strives for, and hopefully has achieved to some extent.
I can add my user perspective about the Chapel community. Like I think I heard about it first time like half year ago, little before Cuba, and then I just joined. So Cuba is like, you know, this yearly Chapel conference meetup. And I just joined it, and you had this like coding day, which it seemed like a pretty cool idea, but at the time I had written like 0 Chapel code. So when I subscribed, I just wrote there was like this questionnaire, like what kind of things would you like to do? And there was like no particular ideas. I don't know anything about Chapel, so just like general like interactive chatting, like chill overview. And I mean, it was pretty cool. I remember, I think you also were there at the coding day, like at my session. Then there was like this army of trainees or like interns like helping. So it was like very cozy and very cool that I was like 0 experience. So like pretty much like my answer, like, I don't know anything. It's, you know, like by the book, the bad way to ask for help, but still like there was everyone helping me and coding together, like live stream. So it was very fun. That's something I really enjoyed.
Yeah, and we'll hope to do that coding day again this year. That workshop usually takes place kind of in the May to June timeframe. I think we're going to be virtual again this year, or even if we're in person, there will be a virtual component to it. And so I think the plan is to do that coding day again. But again, I'll also mention, as I did in the previous slide, like, you know, if somebody has a user or a use case they'd really like to explore in Chapel, there's no need to wait for that coding day to occur. We can do these kind of pair programming sessions anytime. Well, until we're so popular that we don't have the resources to keep up with it anymore. But at this point, we definitely are encouraging those kinds of interactions. So.
Yeah, great. I don't see other questions in the Hackathon. I don't know if there are other questions from the audience, or if there's some. Okay.
And if not, again, I just have a few slides sort of illustrating some of those GPU features I mentioned, so I can go ahead and do that now. Does that sound good?
Yep.
All right. Let me find them. They're somewhere back here. My backup slides are kind of my security blanket when I give a talk. Okay. Chapel on GPUs. So as I mentioned before, as you probably know, GPUs have become a key feature in many HPC systems. I think most of the top systems on the top 500 typically have GPUs and rely on them to get their top 500 performance. As you heard me say at the beginning of the talk, forever we've been describing Chapel's goal as any parallel algorithm on any parallel hardware. But for most of the project's history, people would then say, what about GPUs? And we'd say, oh, we don't support those yet. We want to. Happily, we are starting to support them more and more. Well, that said, I should note that even before we had GPU support in Chapel, because we have interoperability, it has been possible to write a GPU kernel in Cuda or OpenCL or OpenMP or whatever, and then just call out to that as an external routine. So we do have users that have made use of GPUs in their computations. It's just that they haven't been able to use Chapel to program the GPUs, and that's what we're trying to address here in order to fulfill this, any parallel algorithm on, at least on GPUs and CPUs kind of part of the story. Again, this is sort of historically, the answer's been no, we don't really support that. But in that last year or year and a half, we've made a ton of progress here. And so I'll show you just a little bit about what that code looks like. This is, let's see, have we seen this? We have not seen this code today. Oh, well, I guess we did see it at a very, very high level. So when I was showing my HPC benchmark slide, one of the examples I showed was stream triad. We didn't really talk about it though. So if you're not familiar with stream triad, it's a very simple computation. You've basically got 3 one-dimensional arrays or vectors, and you're basically doing a scalar multiplication by one of those vectors, adding it to a second vector, assigning it to a third one. And while this is an incredibly toy computation, it sort of is a good example of, again, embarrassing or pleasing parallelism, and sort of, can you create a bunch of tasks and have them drive the memory in an efficient way as fast as possible? So let's see, I think you understand everything about this code now. I guess we didn't talk about these whole array operations. We saw the for all loops, and I mentioned briefly in passing that we have zippered for all loops, so you can iterate over multiple things simultaneously. There's also this form where you can write things that look like these whole array operations, and this is essentially equivalent to a zippered for all loop. So it's kind of like iterating over the arrays A, B, and C in a zippered manner, and then doing these operations element-wise on their components. So if you remember, the for all loop over an array or a domain essentially uses all the cores or processors to which that array or domain is distributed. The same thing is true here. And so since this is just a local array, I haven't used that dmapped clause to distribute it all. These are going to be local arrays. We're just going to use local cores to execute it. And as a result, this is basically, oh, sorry, I forgot I had all these things. This is basically just a multi-core program. So again, I'm not referring to other locales. I'm not using any distributions. And therefore, I'm just using local resources. So I run this in multiple cores. Now, at this point, you all are expert enough in Chapel that you will understand this code. Stream EP, the EP here means embarrassingly parallel. And this is a form of the stream benchmark where each node computes its own stream triad and then sort of drops the result on the floor, more or less. So here what I've done is taken that multi-core code we've seen before and just wrapped this co-for-all on around it. And this is the same pattern you've seen before. We're creating a task for every locale or compute node, and then we're moving that task to its respective compute node, and then we're running the code in the body here, which, again, because it's a multi-core computation, we use all of the cores on that compute node. So essentially, this will have each of my locales allocate its own 3 arrays, do its own parallel computation of those arrays, and drop the result on the floor. So admittedly a toy, but one that's used a lot in benchmarking. And here I'm just saying things I've already taught you about: the co-for-all, the array of locales, and the on clause. This was designed for a different audience. All right, but as I've written this here, this is only going to use the CPUs of the program. Nothing in this code refers to any GPUs on my node, again, either explicitly or implicitly. So next, let's look at what we'd have to change here to make this into a GPU code. And essentially what I've done here is add another co-for-all loop in here. So my outer co-for-all loop is still creating a task per compute node. And then this co-for-all is executing over here.gpus. On a system that has GPUs, this essentially is an array of all of the, we call them sublocales. Each sublocale represents one of the GPUs. And we're basically saying create a task per GPU and then execute that task on its respective GPU. Probably I have some animations here. So yeah, similar co-for-all plus on idiom. We're basically saying run a stream triad on each of the GPUs on this locale. And because we're doing that across all the locales, we basically have, a distributed memory GPU program. However, by rewriting it this way, nothing is really using the CPUs other than the code just that's required to get these tasks up and running. So I'm basically wasting my CPU resources. So at this point, I can introduce a concept that you haven't seen yet, the co-begin. I mentioned there are a couple of other ways of creating tasks in Chapel. One of those is this co-begin statement. This is essentially a compound statement where each of the child statements will be executed as a separate task. So this code begin has two child statements. The first is my code for all for the GPUs that we saw before. And the second one is basically just a little statement that does the stream triad the way I originally started out doing it. And so because there are two statements in this code begin, I'm going to create two tasks, one to do the GPU section and one to do the CPU section. And then each of those tasks is going to spin up additional tasks. My code for all here is going to spin up tasks across all my GPUs. And then again, the whole array operations here are going to be implemented by default across all of the cores on my CPUs. And probably I've got some more callouts here. Yeah, so basically we're creating a task for the GPU triad, another task for the CPU triad, and then we use, again, the concepts we've already seen to create explicit task parallelism for the GPUs or the implicit data parallelism for the CPUs. And at this point, if I ran this on 1,000 nodes, I'd be using all of the cores and all of the GPUs across all 1,000 nodes to compute a stream triad, and then admittedly just drop it on the floor. So obviously, for real computation, what you would see in addition to this would be some copies of variables from the GPU to the CPU. Maybe I'm like copying some data over to the GPU, computing on it, copying it back. That copying is done just through assignments of variables declared outside of the GPU on clause or inside of it. And we've written codes that are more sophisticated than this, but this is sort of a nice one for slides, just to kind of demonstrate how the features you've already seen can be composed and used to program GPUs without sort of major changes to language. So let me pause there and see if there are any questions. I think I've got one slide for wrap up maybe, but yeah, I've sort of thrown a lot of stuff at you here. Any questions here?
So basically, is it so that heterogeneous CPU GPU programming comes also for free? Just have one task for the GPU, one for the CPU, and then without any further tweaking, or?
Yep, that's right. And one of the things you'll note here is that the CPU code gets to use these high-level arrays and data parallel array operations. Whereas for the GPU operation, at least as I've written it today, I'm using what we call the lower level features of Chapel, the explicit code for all loop. So I'm explicitly creating tasks. I'm explicitly saying to run them on the GPU. One of the directions we want to take this is, I mentioned earlier that these array implementations, these domain maps, can be written in the language by an end user. And so something we don't have today but are building up to is, you can imagine a domain map that would say, well, declare these arrays distributed across my GPUs. And then you could potentially write the same kind of high-level code for the GPU, where the only change would be that rather than just 1 to n to declare these arrays, I would say 1 to n dmapped to my GPU-based distribution or whatever. And then their implementation, their allocation would all be governed by that domain map. And then we could use the high-level for all loops or these whole array operations to drive all the GPUs. Again, we don't have that yet today. We're sort of building up from very explicit things to the higher level things. So today, the way to do it is using the lower level features in Chapel. But again, over time, you should expect the GPU code to look more and more like the CPU code. And you could even imagine a domain map that sort of said, distributed my arrays and their iterations across both GPUs and CPUs using this ratio or something like that, and just sort of drive the whole thing with one whole array operation. But that's even kind of further off into the future, but very tractable. Any other questions or comments here?
I don't see Hakam Deer in the chat. Any questions coming?
So what do I have here? Let's see. Oh yeah, so what's next? So first of all, I want to re-emphasize this GPU support is quite new, and we would definitely call it sort of still in a prototypical phase. It has been released, and our next release is just a couple of weeks away. So if you're interested in using GPUs and trying out these features, you can do that with our last release or with this upcoming release. I just want to, again, add the caveat that, it's still early days. If things don't quite work right, please let us know. We appreciate hearing that from users and particularly understanding where things aren't working for you or aren't working as well as you would like. Some of our next steps here in the short term are, performance on these GPU codes is sometimes great and sometimes it's not so good. And we're still trying to understand what differentiates the good cases from the bad cases and what improvements do we need to make the bad cases perform better. Today, we only support NVIDIA GPUs in our current release, although our upcoming release is going to have some initial support for AMD GPUs as well. And ultimately, we want to support Intel GPUs. So portability across GPU vendors is a key concept here. but it's still early days there, where so far NVIDIA has gotten a lot more attention than the others, primarily because NVIDIA is sort of what a lot of our users are using the most. And then the other thing is, we haven't talked much about communication today. Actually, we haven't really talked about it at all. But in Chapel, communication is expressed by just referring to variables that happen to be allocated on a different locale. So rather than explicit sends and gets, or sends and receives, or gets and puts, you just refer to a variable, and if that variable happens to be remote, that generates communication. Today, the GPUs can communicate with the CPU memory just by copying variables back and forth, but there's no way for a GPU on one node to communicate with a remote node or a remote GPU on that other node. And that's something that some of our users would like, to have GPUs basically be kind of full first-class members, not just sort of a limited sublocale, but kind of like a full featured locale in Chapel. And so that's something else that we're working on going forward. And yeah, that's actually where I had planned to stop this little sidebar. So I'll pause there again and see if there are any questions. And if not, that's what I've prepared for you for today. And again, thanks very much for the invitation to speak to you today, and particularly for your interest with the questions, and for those of you who've been able to hang around longer and hear this sort of extra stuff. Any final questions there, Luca? Or anyone else?
I don't see questions in HackMD, but I don't know if someone can also speak up. Okay, so otherwise, thank you very much for the talk, and this will come to the Nordic-RSE YouTube channel also soonish, and I can now stop the recording. Great.
And yeah, if anybody has any other questions,
yeah, go ahead. I have.
We're still there. Okay, sorry, yeah. my thing froze. So yeah, if anybody has any other questions, first of all, if you didn't want to ask them on camera, happy to stay after a few more minutes to answer those. But also, I've put back up here again various ways you can interact with us through Discourse, which is like a mailing list web-based forum, if you will. Gitter, which is a real-time chat. Stack Overflow, which you're probably familiar with if you have kind of Q&A types of things. And then GitHub Issues is a way of filing feature requests or bugs. After today, these are great ways to interact with us. There's also an email address you can find on our website. So yeah, reach out if there's anything after today that you'd like to know more about. But yeah, any questions off camera anybody wanted to ask? Yeah, so I'm now stopping.